Here's sac216, problem number 3. You get a bar magnet suspended by a silk thread and a magnetic field. Here's the magnetic field represented in green. Bar magnet right here with its north end being the one that's got the arrowhead on it. And the silk thread would be coming out of the page at you. You can't see the silk thread. We're looking down on this from above. The silk thread exerts no torque on the bar magnet. They give us this orientation, 18 degrees with respect to the magnetic field, the orientation of the bar magnet, and they want us to find the angular acceleration of the bar magnet. The concept is you put a bar magnet in a magnetic field, and the magnetic field exerts a torque on the bar magnet, which tends to cause the magnet to spin around so that it lines up with the magnetic field, points in the same direction as the magnetic field. So in this case, as viewed from above, we're going to get a counterclockwise torque exerted on this bar magnet. The equation that summarizes that concept, that a magnetic field exerts a torque on a bar magnet that's in it, as long as the bar magnet is not already pointing in the same direction as the magnetic field is, torque is equal to mu cross B, where mu is the magnetic dipole moment of the bar magnet and B is the magnetic field in that region of space where the bar magnet finds itself. So torque depends on a characteristic of the victim and a characteristic of the space that it finds itself in. For case at hand in magnitude, we can say torque is mu B times the sine of theta. By definition of the cross product, we've got mu cross theta B in magnitude. The cross product of two vectors is the magnitude of the first one times the magnitude of the second one times the sine of the angle in between. And I think that's as far as we need to go with figuring out what that torque on it is going to be. And now we'll turn to Newton's second law for rotational motion, which says that the torque is related to the angular acceleration by torque is equal to I alpha. This is going to be the net torque in a particular direction. We'll call it, say, a counterclockwise torque. And we've got in order for this to have meaning, for the net torque, we can say the sum of all the torques about some point O in the counterclockwise direction is going to be equal to the moment of inertia of the object times the angular acceleration of that object about that same point O. We need a free body-like diagram, one for the torques. And let's go ahead and get a free body-like diagram. I'll tell you why I call it free body-like instead of free body. I'll go ahead and call that point where the thread makes contact with the bar magnet, point O. And the magnetic field, we said, is going to tend to rotate this thing counterclockwise, so it's exerting a torque, which is counterclockwise about point O on that bar magnet. And as a result, the bar magnet experiences some angular acceleration. Now, the reason I call it a free body-like diagram is I'm leaving off some of the forces that are difficult to draw in here and not relevant to the torque. That is, the thread exerts an upward force, a force that in this diagram would be out of the screen at you, or out of the page at you if you're copying this down on a piece of paper. And the Earth's gravitational force is also being exerted on this bar magnet and is pulling it downward toward the center of the Earth, which in this picture is into the page. Because they both act through point O, they supply no torque. They're fairly irrelevant to the problem. I'm not going to include them on there, and that's why it's not a complete free body diagram, but it is still just what I need. So the net torque counterclockwise about point O, there is only the one torque. Due to the magnetic field, I'll just call it tau, and that's going to be equal to I times alpha. The torque we found is mu B sine of theta. So I'll go ahead and make that substitution. and then I'm in a position to solve for alpha. So alpha mu b sine of theta divided by the moment of inertia of the object. Remember, that's the inherent resistance to a change in how fast it's spinning. And go ahead and substitute the values in there. We're given mu as 0.90 ampere meters squared, B as 17 microtesla, or 17 times 10 to the minus 6 Tesla, and the angle we were given is 18 degrees. Divide all that by the given moment of inertia, 7.6 kilogram meters squared, and I get alpha as 6.22 times 10 to the minus 7th, which rounds off to 6.2 to 2 sig figs, since everything here is given to just 2 sig figs, times 10 to the minus 7th. And I'll go ahead and put down what alpha is supposed to come out in, and then we'll work out the units and make sure it really does. It should come out in radians per second squared. Let's see what we've actually got there. We got ampere meter squared times Tesla, where a Tesla is a Newton per amp meter. And then this is a pure number, and I've got kilogram meters squared in the denominator there. So let's see, the amperes cancel out. These meters squared cancel out. And a Newton is a kilogram meter per second squared. So these meters cancel out, and now the kilograms cancel out. I'm left with just 1 over second squared. And the radian, remember, that's a fraction of a circle. It's not a true unit. Where needed, you can pepper that in with care, and indeed we can just add the radians called the angular acceleration, 6.2 times 10 to the minus 7th, 1 over second squared, which is the same thing as 6.2 times 10 to the minus 7th radians per second squared. And that does it for SAC 216, problem number 3.